A signal leaves Earth right now. Not a rocket, not a probe, just light, the fastest thing the universe permits. It crosses the moon in a second and a half. It passes Mars in minutes. It blows past Jupiter before most people finish their morning coffee. And yet, 4 years and 4 months from now, that signal, traveling at nearly 300,000 kilometers per second without stopping, without slowing, without any of the constraints that plague physical objects, will only just be arriving at Alpha Centauri, the closest star system to our own, our nearest neighbor in the entire galaxy. And we can't even get light there in a human-relevant time frame, let alone a spacecraft, let alone a person. That gap between what we imagine and what physics actually allows is what this video is about. Alpha Centauri sits 4.37 light-years from Earth. That number sounds almost modest, 4 point something. People hear it and think, well, we've done hard things before. We went to the moon, we landed rovers on Mars, we sent probes to the edge of the solar system. Surely 4.37 light-years is just the next step up. But a light-year isn't a unit designed for human intuition. 1 light-year is roughly 9.46 trillion kilometers. Multiply that by 4.37, and you get approximately 41 trillion kilometers between us and Alpha Centauri. To put that in perspective, if you shrank the entire solar system, Sun to the edge of Neptune, down to the size of a dinner plate, Alpha Centauri would be about 140 meters away. Not across the table, not across the room, down the street. And that's the closest one. Every other star is farther, most are vastly farther. This is where reality kicks in. The dream is legitimate and worth acknowledging. Projects like Breakthrough Starshot have proposed sending laser-propelled nanoprobes to Alpha Centauri within a generation. Scientists and futurists have spent serious time and money exploring the idea. Science fiction has conditioned us to see interstellar travel as the natural next chapter of human civilization. In the cultural imagination, Alpha Centauri is the first stop, the proof of concept, the moment humanity graduates from a single star species. And if you're going to dream of anywhere, dreaming of our nearest stellar neighbor isn't naive, it's logical. There's even a planet in the habitable zone of Proxima Centauri, the third star in that system. Proxima b, a rocky world that could, under the right conditions, hold liquid water. The dream has a destination, it has a face, it has a reason. But here's where it gets interesting. The fastest human-made object ever recorded is the Parker Solar Probe, which hit approximately 692,000 kilometers per hour during a close solar flyby. That number is genuinely staggering. It is faster than anything humans have ever built. At that speed, you could circle Earth in under 4 minutes. And at that speed, a journey to Alpha Centauri would take approximately 6,300 years, not generations, not centuries in the romantic epic novel sense. 6,300 years. The ancient Egyptians were building the first pyramids roughly 4,500 years ago. We would need to travel longer than that, and then some, just to reach our nearest neighbor, using the fastest technology we have ever produced. And that's the Parker Solar Probe, which achieved that speed through gravitational assists from the sun, a trick that only works in the inner solar system. A ship heading outward doesn't get that boost, it slows. Voyager 1, which has actually left the solar system and is the farthest human-made object in existence, travels at around 61,000 kilometers per hour. At Voyager's speed, Alpha Centauri would take roughly 73,000 years. Voyager launched in 1977. Homo sapiens as a species has only existed for about 300,000 years. We are talking about a journey that would consume a significant fraction of our entire species' history, and we haven't even talked about the energy required. Every proposed solution to the propulsion problem carries a fatal flaw buried inside it. Chemical rockets, the kind that got us to the moon, are essentially controlled explosions. They're magnificent for escaping a planet's gravity well, but they top out at speeds that make interstellar travel a geological-scale enterprise. Ion drives are more efficient, but produce thrust measured in millinewtons, enough to gradually accelerate a small probe over years, not enough to push anything carrying humans to meaningful fractions of the speed of light. Nuclear pulse propulsion, which would essentially detonate a series of nuclear bombs behind a spacecraft, is theoretically capable of reaching perhaps 3 to 5% of light speed. At 5% of light speed, the journey to Alpha Centauri would take roughly 90 years. 1 lifetime, barely. But the fuel mass required is staggering. The engineering has never been attempted at scale, and even if it worked, 90 years of interstellar travel introduces a different category of catastrophe entirely. Fusion drives, antimar, ITER engines, laser sails, each one runs into the same fundamental problem. Either the energy requirement is physically impossible to meet with anything we can launch from Earth, or the technology doesn't exist and has no clear engineering path toward existence, or the system is so fragile that a single failure in deep space means the mission ends with no possibility of rescue. The rocket equation is unforgiving. Every kilogram of fuel you add requires more fuel to accelerate that fuel, which requires more fuel to accelerate that fuel, and the math spirals into absurdity very quickly. You don't solve the propulsion problem by wanting it hard enough. You solve it by rewriting physics, and physics doesn't take requests. Even if propulsion were solved, the human body was not designed, was not evolved, to survive the journey. Galactic cosmic rays are the first thing that will begin dismantling you. Outside the Earth's magnetosphere, you're exposed to a continuous bombardment of high-energy particles accelerated by supernovae and other stellar catastrophes across the galaxy. These particles don't just pass through you, they break chemical bonds in your DNA. They knock electrons out of atoms inside your cells. Over months, the cumulative damage accumulates beyond what your body's repair mechanisms can handle. The risk of developing fatal cancers during a multi-decade interstellar voyage isn't a statistical footnote. It's a near certainty with current shielding technology. No known material provides full protection without adding mass so enormous it defeats the propulsion math entirely. Your bones begin losing density at roughly 1 to 2% per month in microgravity. In a year, you've lost the bone mass equivalent to a decade of aging on Earth. In 10 years, your skeleton resembles that of someone in late-stage osteoporosis. Your muscles follow. The heart is a muscle, and in microgravity it has less to do. Blood redistributes toward the head, fluid pressure increases behind the eyes, and the optic nerve begins to swell. Astronauts returning from 6-month missions on the International Space Station have documented measurable changes to their eyeball shape. Not temporary pressure, structural change. On a 90-year mission, these aren't risks, they are outcomes. Then there is the psychology. Isolation research suggests that humans in confined environments, cut off from natural light cycles and separated from the rest of their species, begin experiencing cognitive deterioration, interpersonal conflict, depression, and psychosis within months. Studies from Antarctic winter over stations, from submarine deployments, from simulated Mars missions, all point to the same conclusion. The human mind did not evolve for the void. We are social, terrestrial creatures, and placing us in a metal cylinder for 90 years surrounded by nothing on all sides produces psychological damage that compounds across generations if you're running a generation ship, or simply destroys the crew if you're not. And then the cascading failures begin. Life support on a spacecraft isn't a background and system. It is the entire mission. Water recycling, air recycling, food production, thermal regulation, radiation management, and power generation all depend on components that can fail. On the ISS, resupply missions arrive every few months. A part breaks, a new one arrives. On an interstellar voyage, the nearest hardware store is several trillion kilometers behind you. Every component must be manufactured on board or done without. The communication delay between Earth and a ship 1 light year out is 1 year each way. If you send a distress signal, the response arrives 2 years later, minimum, and the response is only words. Nothing physical can follow it. You're alone in a way that no human crew has ever been alone, troubleshooting failures in systems that have never been tested for decades of continuous operation, with no margin for error and no possibility of rescue. Micrometeorite impacts, cosmic ray damage to electronics, solar energetic particle events, long-term material fatigue. These aren't hypothetical dangers. They are statistical certainties across a journey measured in decades. One breach, one critical system failure, one moment where the redundancies all fail simultaneously, which they will eventually, given enough time. With everything we know about physics, engineering, biology, and human psychology, a crewed mission to Alpha Centauri using any technology we have or any technology with a plausible engineering path forward is not a hard problem. It is not a funding problem or a political will problem. It is a problem built from the structure of the universe. The distances are too vast, the energy requirements too enormous, the human body too fragile, and the systems too complex to survive for the necessary duration. This isn't pessimism, it's arithmetic. What remains is something quieter and, in its own way, more remarkable. We are the only thing in the known universe that looks up at Alpha Centauri and knows exactly how far away it is, exactly what kind of stars it contains, exactly how long it would take to reach, and feels the ache of not being able to go. That capacity, the mathematics, the telescopes, the understanding, the longing, that is not nothing. That is, arguably, the most extraordinary thing that has ever happened on this pale, fragile planet. We may be confined to one star system for the entirety of our existence. We may never touch another sun, but we can see them, we can measure them, we can understand them in ways that took 4 billion years of biology to make possible. And somewhere in that understanding, there is something worth protecting, worth celebrating, worth continuing. We may never reach Alpha Centauri, but we named it, we studied it, and we knew exactly what we were missing.